Ever dreamt of hopping on a supersonic jet and reaching your destination, like in a flash? It feels like we're on the cusp of a supersonic comeback, doesn't it?
It really does.
But how do engineers actually design these marvels of speed? Well, get ready to deep dive into that very question,
Yeah.
because we're looking at a PhD thesis all about simulating the wild world of supersonic airflow.
And this isn't some dusty old research paper. This
Yeah.
thesis was written in 2017, practically yesterday, in the world of scientific research.
Wow.
It's like taking a peek into the recent past of supersonic design.
A supersonic time capsule. I like it.
All right.
So before we get into the nitty-gritty of simulations, let's talk about the elephant in the supersonic room. Why is it so darn hard to break the sound barrier in the first place?
It all boils down to drag. That invisible force that resists an object's movement through the air. Now here's where it gets interesting. Drag doesn't just increase proportionally with speed.
Right.
You might think, double the speed, double the drag, right?
Seems logical enough.
Not quite. It actually increases exponentially.
Okay.
So to hit those supersonic speeds, you need a mind-boggling amount of extra power.
Wow.
Just to overcome that wall of resistance.
Okay, that's already making my head spin a bit. So it's not just about strapping a bigger engine onto a plane.
Yes.
It impacts the entire design, doesn't it?
Absolutely.
Yeah.
For one, supersonic aircraft need to fly insanely high, where the air is thinner
Right.
and offers less resistance. They also need to be incredibly aerodynamic. Think those sleek, almost needle-like designs you see on supersonic jets.
Right.
Every curve and bump is minimized to cheat the drag.
Right. Like the Concorde, speaking of which, the thesis actually compares the Concorde's performance to a Boeing 747.
Right.
And the results are not what you might expect.
It's a striking comparison, really. The Concorde, despite being an incredible feat of engineering, had an aerodynamic performance ratio of about 7.14.
Okay.
That's the ratio of lift, the force that keeps it in the air, to drag. A Boeing 747, on the other hand,
Right.
boasts a ratio of 17.
Wait, so the Concorde is actually way less efficient than a jumbo jet. That's wild.
It highlights the immense difficulty in achieving efficient supersonic flight,
Yeah.
even when you've managed to crack the code of breaking the sound barrier. But even beyond drag, there's another major player that throws a wrench into supersonic design. Shockwaves.
Yes, those invisible walls of air that seem to plague supersonic flight. What's the deal with shockwaves, anyway?
Imagine this. As an object approaches the speed of sound, the air molecules in front of it don't have time to get out of the way. It's like trying to squeeze a crowd through a doorway all at once.
Chaos.
Exactly. And this creates a sudden dramatic increase in pressure. A shockwave. Think of it like a sonic boom you can't hear yet.
Right.
But it's putting immense stress on the aircraft. And these shock waves cause a massive spike in drag. We're talking a 4-fold increase at transonic speeds right around that sound barrier.
4 times the drag. So wonder getting past that speed bump is such a challenge.
Right.
And here I thought supersonic flight was just about having a powerful enough engine.
If only it were that simple. Even at full supersonic speeds, where the aircraft is cruising faster than the speed of sound, shockwaves are still a major factor in design and efficiency. They're just not quite as extreme.
Okay, so shockwaves equal bad news for speed and efficiency.
Yeah.
Got it. But how do engineers actually design around these invisible troublemakers? That's where this thesis comes in, right?
Yeah.
It's all about simulating these complex aerodynamic forces to make supersonic flight more, well, flyable.
You've hit the nail on the head.
Okay.
By understanding and predicting how air behaves at these incredible speeds, we can design safer, more efficient,
Right.
and maybe even quieter supersonic aircraft in the future.
So how do you go about simulating something as invisible and chaotic as airflow, especially at supersonic speeds?
That's where the magic of computer simulations comes in. This PhD thesis focuses on something called finite volume methods.
Okay.
Sounds intimidating, I know, but the core concept is actually quite clever. Imagine dividing the space around a plane into millions of tiny cubes, almost like a 3D grid.
Okay, I'm picturing these tiny boxes of air surrounding the plane. What happens next?
Each cube represents a small volume of air, and the simulation calculates how the air inside each cube, its pressure, speed, direction, is affected by the air in the surrounding cubes.
So it's kind of like a giant game of dominoes, but on a microscopic level. Each cube influences its neighbors, and the simulation tracks all those tiny changes.
Exactly. And by repeating these calculations millions of times at incredibly fast speeds, you can create a detailed picture of how air flows around an object in flight. But here's the thing. You might be wondering why use this specific method, finite volume methods.
Yeah.
Why not something else?
You've piqued my curiosity. What makes this method particularly well-suited for supersonic flow?
Well, traditional simulation methods often stumble when it comes to those abrupt, dramatic changes in pressure caused by shock waves. They're good at modeling smooth, continuous flow, but shock waves throw a real wrench in the works.
Yeah.
Finite volume methods, on the other hand, are better equipped to handle these sudden shifts because they focus on the conservation of physical quantities, things like mass momentum and energy within each of those tiny volumes.
You're saying they're designed to keep track of those sudden jumps in pressure like what you see with a sonic boom.
Precisely. And that makes them invaluable for simulating the complexities of supersonic airflow. And this type of simulation isn't just limited to supersonic jets. You can use it to design anything that moves through air or even water, from fighter jets and rockets to submarines and even your car. These simulations help engineers optimize for speed efficiency and performance.
Wow. It's amazing to think that something as seemingly abstract as a mathematical model can have such a tangible impact on the design of real-world objects.
It really highlights how crucial this type of research is. This PhD thesis might be focused on supersonic flight, but the applications of this work extend far beyond that.
So we can simulate smooth airflow, which is already incredibly complex in itself, but we've talked about how shock waves are a whole other beast. They're chaotic, unpredictable. How do you even begin to wrangle those into a simulation? That's the million-dollar question, isn't it? It's one thing to model smooth airflow, but capturing the chaos of shock waves, that sounds like a real programming nightmare.
It is incredibly challenging. Even with advanced methods like finite volume methods, standard simulations can still become unstable when those sudden drastic pressure changes come into play.
So the simulation itself can't handle the shock wave. It's like the math equivalent of a blue screen of death.
You're not far off. Think of it this way. Simulating smooth airflow is like trying to capture a perfectly still pond on camera.
Okay.
It's straightforward and predictable, but a shock wave is like a massive rock suddenly plunging into that pond, sending shock waves across the surface. It's a completely different beast to capture.
Okay, I'm starting to understand the difference in scale and complexity here. So how did this PhD candidate tackle this shockwave problem? Did they find a way to make the math less allergic to sudden changes?
That's a great way to put it. They actually developed an ingenious hybrid system,
Okay.
a simulation that could seamlessly switch between two different modes. One mode handles the smooth, predictable parts of the airflow, while the other kicks in specifically when shock waves form, providing extra stability and accuracy where it's most needed.
So it's like having a camera that can flawlessly switch between recording a tranquil scene and capturing a sudden explosion, all without missing a beat.
Precisely. This hybrid system is a game changer for engineers because it allows them to see the intricacies of supersonic airflow, even with those dramatic shock waves present. It's like having X-ray vision for supersonic flight.
This hybrid system sounds like a huge breakthrough. But how do you know if these simulations are actually reflecting reality? It's not like you can just fly a plane through a shockwave and compare the results.
You're right, you need rigorous ways to validate these simulations to make sure they're not just spitting out random numbers. That's where the real genius of this thesis comes in. The author put their hybrid system through a battery of tests, two of which are particularly fascinating.
Oh, I love a good test. What did they do?
One test is called the isentropic vortex. Imagine a mini hurricane, a perfectly formed, swirling vortex of air contained within a virtual wind tunnel.
Okay, I'm picturing a tiny tornado in a digital bottle.
Exactly. The simulation tries to replicate this vortex as it moves, and the goal is to see how much the simulation smears the vortex over time. Ideally, it should stay crisp and well-defined.
So less smearing equals a more accurate simulation.
Exactly. More smearing means the simulation is introducing artificial diffusion, essentially blurring the details of the airflow.
Got it. What about the second test?
This one gets even closer to real-world supersonic flight. It's called the supersonic cylinder. Picture a cylinder sitting in a wind tunnel with air blasting past it at supersonic speeds.
Okay, I've got the visual. What happens next?
As you can imagine, the supersonic air slams into the cylinder, creating those telltale shock waves, just like a plane breaking the sound barrier.
Right.
This test pushes the simulation to its limits to see if it can handle those sudden, intense pressure changes without breaking a sweat.
So it's like a digital crash test, but for supersonic flight.
That's a great analogy. And the fact that the author took the time to validate their simulation with such realistic tests shows just how dedicated they were to solving real-world problems, not just tinkering with equations in a vacuum.
It makes you appreciate the dedication and ingenuity that goes into this kind of research.
Absolutely. Now, you might recall that this thesis specifically focuses on transonic speeds, the speeds right around the sound barrier. Why is this such a crucial area of focus?
It sounds like the sweet spot, or maybe the sour spot, considering how much trouble it gives engineers.
That's a great way to put it. Transonic speeds are where things get really messy because the airflow is in a constant tug of war between smooth subsonic flow and chaotic supersonic flow. You have these pockets of different speeds all interacting with each other, and those troublesome shock waves are forming and dissipating.
So it's like trying to predict the weather, but on a microscopic level around an object traveling hundreds of miles per hour.
An apt comparison. And yet, the author of this thesis successfully simulated transonic flow over a virtual airfoil, which you can think of as the cross-section of a wing.
So they were able to model what happens to a wing as it approaches and even breaks the sound barrier. That's incredible.
It's a huge step forward in our understanding of transonic aerodynamics. However, and this is crucial, the author acknowledges that even their sophisticated hybrid system isn't perfect. It can't capture every single microscopic swirl and eddy of turbulent airflow, especially in that chaotic transonic regime.
So even cutting-edge simulations have their limits. That's kind of humbling, isn't it?
It is. It reminds us that there's always more to learn and that even the most sophisticated models are just approximations of reality.
This has been an incredible deep dive. It's amazing to think about all the complex math and science happening behind the scenes just to get a supersonic jet off the ground. But where does this all go from here? If even the best simulations have limitations, what does the future hold for supersonic design?
That's the question that keeps researchers and engineers up at night. The author of this thesis points out the pressing need for even faster, more efficient, and more accurate simulation methods, especially for tackling high-order problems like predicting the noise generated by supersonic flight. Remember how notoriously loud the Concorde was?
It was practically deafening. So you're saying that better simulations could be the key to quieter supersonic jets in the future?
Absolutely. With advances in computing power and the development of new algorithms, quieter, faster, and maybe even more fuel-efficient supersonic travel might not be a distant dream. It's a thrilling time to be following this field, wouldn't you say?
Absolutely. It makes you wonder what incredible breakthroughs are just on the horizon. Thanks for taking us on this incredible deep dive into the world of supersonic dreams and the numerical realities that make those dreams take flight.
My pleasure. It's always a pleasure to explore these fascinating topics.